Hello, welcome back. In this lecture, we are discussing about the worst possible condition or worst combination of vertical and horizontal inertia forces over the gravity dam, in which we are dealing with the horizontal earthquake force in the upstream direction and horizontal earthquake force in the downstream direction, as well as vertically earthquake force in the upward direction as well as vertically earthquake force in the downward direction. So this is the worst combination of vertical and horizontal inertia forces while the dam has been newly constructed and the reservoir has not been yet filled. Now under the reservoir is in full condition, the worst combination of the inertia forces is one which tries to topple the dam forward. In the previous case, the dam is topple backward direction. Now when the reservoir in full condition, inertia forces is trying to topple the dam in the forward direction. So here is the case. As you can see, this is the horizontal force in the upward direction, HU in the upstream direction, and this is the horizontal earthquake force in the downstream direction, and this is the vertical force in the upward direction, and this is vertical earthquake force due in the downstream direction. So this is your worst combination: vertical upward forces and horizontal downstream forces, which are going to move the dam in the upstream direction, or these are going to topple the dam in the forward direction. But in the previous case, as you can see in the previous diagram, the vertical component of the vertical earthquake force in the upward direction and horizontal component of horizontal earthquake pressure in the upstream direction are making the worst combination under reservoir empty condition, and these are trying to cause the dam to topple backward. So these are the worst combination cases. Now, after the earthquake forces, the next forces acting on a gravity dam is the wave pressure. The wave is generated due to the shearing action of wind blowing over the surface of water which is filled in the reservoir, and these waves put a pressure on the upstream side of dam and downstream side of dam as well. If there is a tailwater in the downstream direction, the pressure of the waves against massive dams of appreciable height is not of much consequences, because the dam is actually massive in construction and having appreciable heights. But for the dams of lower height and not massive, the height of wave is more important in determination of the freeboard requirements of dams. Freeboard requirement is nothing but the difference between the top of the dam and the free reservoir level. The height of wave is given by this formula: HW is equal to 0.34 under root f plus 0.76 minus 0.26 f raised to power 1 by 4, where h subscript w is nothing but the height of wave uh, crest to toe. That means the largest difference between the succeeding two vertices, one is the crest and one is the toe, and This value of height of wave is recorded in meters, and f is nothing but the fetch of reservoir. This is the longest straight distance of the reservoir from the dam up to the farthest point of the reservoir. And this formula given by Stevenson, so this formula is known as the Stevenson formula, and it is only for when it is valid only when the value of fetch of the reservoir is not exceeding 20 kilometers. But what if the fetch exceeds 20 kilometers? The above formula can be approximated as height of wave is nothing but equal to the 0.34 square root of f under root of f. Here is the formula. Now, in the wave pressure, when the height of wave is calculated, the incorporation of wind velocity in the wave of height will lead to the modification of the previous formula, which is replaced by f is replaced by the product of v and f, and sw is nothing but the 0.032 square root of vf plus 0.76 minus 0.26 average to power 4, where v is nothing but the wind speed along the fetch in kilometers per hour, and the pressure intensity due to waves in kilonewton per meter square is given by this expression, and which is the Pw is equal to 23.544 Hw, where Hw is the height of wave in meters, and this pressure occurs at the height of 1 by 8 Hw above the still water level, or you can say 0.125 Hw above the still water level. So you have to remember all these formulas. Now the total wave pressure Pw per unit length. Here is the pressure intensity. Don't confuse in the pressure intensity and the total wave pressure. And here is the total wave pressure per unit length in kilonewton per meter of the dam is given by the Pw is equal to 20 Sw square.